Gravitation and quantum theory as emergent phenomena. Quantum theory without classical time as a route to quantum gravity and unification. I would like to thank my collaborators without whose participation this research program would not have been possible. Spacetime, vector bundles, fermions, dynamics. Our knowledge of physics. In the words of Edward Witten, if one wants to summarize our knowledge of physics in the briefest possible terms, there are really three fundamental observations. Spacetime is a pseudo-Riemannian manifold M endowed with a metric tensor and governed by geometrical laws. Over M is a vector bundle X with a non-abelian gauge group G. Fermions are sections of S plus cross VR, some S minus cross VR bar. R and R bar are not isomorphic. Their failure to be isomorphic explains why the light fermions are light and presumably has its origins in a representation difference delta in some underlying theory. All of this must be supplemented with the understanding that the geometrical laws obeyed by the metric tensor, the gauge fields, and the fermions are to be interpreted in quantum mechanical terms. We would like to bring these three observations into a unified fold, and for that we move on to trace dynamics, octonions, and unification. What are the new ingredients for unification which we now present? Adler's pre-quantum theory of trace dynamics, which is a matrix-valued Lagrangian dynamics. Octonions as a non-commutative spacetime manifold instead of R4, the familiar four-dimensional Lagrangian spacetime manifold. Chomsky-Cohn's spectral action principle, Dirac operator instead of metric, and hence a new Lagrangian which is the trace of the square of the Dirac operator. Exceptional Lie groups for symmetry, in our case that will be E8 cross E8, and Clifford algebras made from octonionic maps for describing elementary particles. Evolution in terms of Cohn's time, a new concept of time available only in a non-commutative geometry and derived from the Tomita-Takesaki theory. There is no change in energy scale vis-a-vis Witten's remarks, our knowledge of physics, and it is the same physics which is being presented in a different formalism driven by the motto that fermions must be described on a spinor spacetime as opposed to on a Minkowski spacetime as is done in quantum field theory, and when we do that we gain additional insights about gravitation and about the standard model. Looked at in another way, the ingredients for unification are as follows. On the four-dimensional Minkowski spacetime, which is curved by gravitation, there live fermions and standard model gauge fields, the latter described by a vector bundle. We are saying, let us take the square root of this four-dimensional Minkowski spacetime in the same spirit in which we take the spirit of the square root of the Klein-Gordon equation to arrive at the Dirac equation. Let us also take the square root of the Minkowski spacetime, and when we do that, we arrive at a spinor spacetime, also thought of as a twistor space described by complex numbers. We next replace complex numbers by quaternions and then subsequently by the octonions to arrive at a complex bioctonionic space in which we have a Lagrangian with a E8 cross E8 symmetry. On this space, the complex bioctonionic space, we have unification of gravitation, pre-gravitation, and the standard model gauge fields as well as the fermions all together described as a geometry, and in reality at all energy scales fermions live in this octonionic space. Their description on a Minkowski spacetime is only an approximation. When we move down by taking this square root, there is no change in energy scale. Just as when we take the square root of the Klein-Gordon equation, there is no change in energy scale involved. There is just a better description of fermions, and the same spirit is being applied to the space-time as well. From Newtonian dynamics to trace dynamics, we are familiar that the action principle for a free particle in Newtonian dynamics on absolute three-dimensional physical space is the kinetic energy integrated over absolute time. So this is the Lagrangian. Now, to go over to trace dynamics, we replace the real number dynamical variables Qi by matrix valued variables Qi bold. Now, the total action of the universe is the sum over all degrees of freedom of integral over a new time, which we call Cohn's time. The position variables had been replaced by matrix valued position variables. The mass has been replaced by a length scale, Lp square by L square in units of Planck length Lp. So the Lagrangian has now become a matrix valued polynomial, and to get a scalar we take a trace. So this is essentially the velocity of the particle in trace dynamics, and we sum over all the degrees of freedom in the universe. What makes trace dynamics special is that it has a novel conserved charge not available in classical mechanics nor in quantum mechanics, and that is denoted by the symbol C tilde, sum over all bosonic degrees of freedom of the commutator QB PB minus sum over all the degrees of freedom the anti-commutator QF PF over the fermionic degrees of freedom. This has the dimensions of action, and this conserved charge is what replaces the Heisenberg algebra of quantum theory, giving us a pre-quantum theory. As you can see, the individual commutators are not constants equal to IH bar, but their sum is conserved. So this is like alternative to the Heisenberg algebra in trace dynamics. From trace dynamics to quantum field theory as an emergent phenomenon. Assume that trace dynamics holds at some time resolution, say tau Planck, which essentially is any time resolution scale not yet accessed in laboratory. This trace dynamics is a Lorentz invariant matrix valued Lagrangian and equivalently Hamiltonian dynamics. We ask, what is the emergent dynamics at time resolutions poorer than the resolution scale tau Planck at which trace dynamics holds? So you are not observing the dynamics as finely, as precisely as in trace dynamics, but in a coarse-grained sense, similar to how we would want to describe water as a fluid if we are not observing individual atomic motions of the water molecules. The techniques of statistical thermodynamics can be used to show that the novel charge just presented in the previous slide gets equipartition. Since the charge is conserved, once it is equipartition, it means the individual commutators QB, PB and the anti-commutators QF, PF, all of them are constant in the coarse-grained sense, and they are equal to each other. Hence, that constant is identified with IH bar. In this sense, the Heisenberg algebra of quantum theory emerges from trace dynamics in a coarse-grained approximation if the underlying theory is not being examined at the time resolution at which it has been proposed. The Heisenberg equations of motion, which are a consequence of averaging the Hamilton's equations of motion of trace dynamics, these Heisenberg equations of motion and quantum field theory emerged from trace dynamics at thermodynamic equilibrium. Away from equilibrium, if the Hamiltonian is originally not self-adjoint, which is how it is assumed to be, under certain circumstances, when sufficiently many degrees of freedom get entangled with each other to form macroscopic systems, the quantum system moves away from thermodynamic equilibrium and the quantum to classical transition takes place, giving rise to the emergence of the classical world. Trace dynamics admits superquantum non-local correlations. As is well known, the CHSH inequality is a version of the Bell's theorem and Bell's inequalities in which the non-local correlations lie between the range 0 to 4. Popescu and Rohrlich showed in a very important paper that if one assumes relativistic causality and non-locality, the resulting upper bound on the Bell-type correlations is stronger than the bound permitted by quantum non-local correlations. The quantum bound is known as the Cyrilson bound and lies between 2 and 2 root 2. The correlation, if it is classical, namely due to hidden variables, is less than 2, it is between 0 and 2. Classical correlations are between 0 and 2. Quantum non-local correlations are between 2 and 2 square root 2. And then there is this very surprising region, namely relativistic causality implies or permits non-local correlations stronger than those of quantum theory, raising a question: is there a relativistically causal theory more general than quantum theory? And recently in this paper, we answered this question in the affirmative, that trace dynamics, so long as the novel charge is not equipartition, trace dynamics can admit superquantum correlations, hence explaining why the PR bound is higher than the Cyrilson bound. It is as if the Cyrilson bound is an attractor at thermodynamic equilibrium. Quantum systems also tend to the Cyrilson bound, and when the novel charge is equipartition, we know that thermodynamic equilibrium is recovered, and then the PR bound comes down back to 2 square root 2. This result suggests that quantum mechanics is approximate and not exact, and is in fact an emergent approximation to trace dynamics. Okay, we have the dynamics. Now we want to choose the Lagrangian for the unified theory. In this, we are aided very elegantly by the Chomsky-Kohn spectral action principle. It is known from the spectral action principle that the Einstein-Hilbert action of general relativity in a so-called regularized heat kernel expansion can be expressed in terms of the Dirac operator on the Riemannian manifold, namely, given a curved Riemannian geometry, write down the conventional Dirac operator on this curved spacetime, take the trace of Lp squared d squared, where Lp is the Planck length. This quantity in a heat kernel expansion is equal to the Einstein-Hilbert action, which hence can also be written as the sum of the squares of the eigenvalues of the Dirac operator on the manifold, because that's what the trace is doing. This tells us, as was shown in an important paper by Landy and Rovelli, that the eigenvalues of the Dirac operator on a manifold can also act as dynamical variables instead of general relativity, instead of the metric of general relativity. So instead of using the metric as a dynamical variable, we use the eigenvalues of the Dirac operator as dynamical variables. And in order to, so this is a classical theory. To go from here to trace dynamics, we must raise the classical real number valued degrees of freedom to the status of matrices / operators. That is what is done now to go to trace dynamics. Each eigenvalue is raised to an operator / matrix lambda I hat, which is our new dynamical variable, the ith dynamical variable, in terms of which a configuration variable QBI is defined, whose const time is equal to lambda I hat. And which is this operator to which it has been raised? The very Dirac operator of which it was an eigenvalue. Hence, corresponding to the ith eigenvalue, we get a trace dynamics Lagrangian, which is integral over const time of trace QBI dot square. So this is the ith eigenvalue, which defines for us an ith atom of space-time. And if we sum over all the atoms, we have to do this sum by summing over all the space-time atoms. So there's a sigma I sum here outside. We have discovered the trace dynamics pre-quantum theory version of general relativity. How will the classical limit be recovered? Each eigenvalue operator, each lambda I hat operator will collapse to one of the eigenvalues lambda I, and then we can sum over all the classical eigenvalues once again to recover four-dimensional space-time and Einstein-Hilbert action for general relativity. So the classical to pre-quantum transition is obtained by raising eigenvalues to dynamical variable operators, and the pre-quantum to classical transition is done by the spontaneous collapse of the operators to the classical eigenvalues. We can include matter now in the theory in the following sense. So this is, we are getting to our fundamental Lagrangian, which describes the unified theory. This part, QB dot dagger, QB dot is the gravitational part, to which we add the the fermionic part described by operators Q dot F dagger and Q dot F. These will play the role of right-handed fermions in the theory, and L is a length scale associated with this atom of space-time matter. There are only three fundamental constants in the theory: Planck constant, Planck time, and Planck length. In terms of these three constants, every other constant, dimensional as well as dimensionless, has to be derived from the theory without any fine-tuning and without any further input from outside. Beta 1 and beta 2 are two constant unequal Grassmann numbers needed to make this Lagrangian bosonic. The matrices QB and QF are made of Grassmann numbers as entries. QB, the bosonic matrices, are made up of even grade Grassmann numbers, and the fermionic matrices are made up of odd grade Grassmann numbers. In this Lagrangian for space-time matter, which has only dotted variables, we can introduce also Yang-Mills fields as the undotted configuration variables corresponding to QB dot and QF dot. So if you see, this is like a potential added to the momentum, as we do in the Dirac operator whenever we want to include a Yang-Mills gauge field. QB dot dagger plus I alpha by L QB dagger. This length scale as well L was already there. Now we introduce the coupling constant of the Yang-Mills theory alpha, and in fact, for example, the fine structure constant will be made from alpha and L, and the other coupling constants and mass ratios are also to be coming out from here. So this is the potential, the Yang-Mills field included. Along with that, we have included the QF dagger variable corresponding to this fermionic velocity. And it turns out that this will describe left-handed chiral fermions, and the corresponding counterpart of this bilinear term, where beta 1 has been replaced by beta 2. In every other respect, the second bracket is the same as the first bracket. This is the fundamental Lagrangian of the unified theory which we have investigated. So we have a dynamics, trace dynamics. We have a Lagrangian motivated by the spectral action principle of Chomsky and Kohns. In the classical limit, when the quantum to classical transition takes place, this Lagrangian can be shown to describe Einstein-Hilbert action, the action for Yang-Mills field, the action for relativistic particles and their currents in the presence of gauge fields, and importantly, a modification to general relativity caused by conformal gravity, which we believe is going to play a very important role in cosmology. So in the classical limit, once Yang-Mills fields are included, in the classical limit, the emergent theory is a modified gravity which has a conformal gravity modification of general relativity. Okay, the next step, we have trace dynamics, we have the Lagrangian, a new coordinate system. Octonions as coordinate systems are non-commutative manifold. A vector bundle and a manifold together are replaced by a space labeled by octonions, 8-dimensional octonionic space. The algebra automorphisms of the octonionic space unify diffeomorph spacetime diffeomorphisms and gauge transformations. But what is important, firstly, in this transition from vector bundle plus manifold to octonionic space, there is no change in energy scale. We have essentially taken a square root of the 4D spacetime manifold, and we have also taken a square root of the vector bundle. Furthermore, the octonionic space is associated not with the whole universe, but with each atom of spacetime matter. So remember, going back to the previous slide, this is one atom of space-time matter, and we have to sum over I to get all the degrees of freedom of the universe. And for most of the rest of the talk, we are concerned with just understanding one atom. This is like vibrations of the string has all degrees of freedom, gauge fields, gravitation, as well as chiral fermion. That's what is going on here. Different vibrations of this, what we call an atom of space-time matter, or two-brane, different vibrations give different elementary particles and gauge fields. Okay, so what we are saying, coming back to this slide, what we are saying is that the octonionic space has one copy for every degree of freedom. This Lagrangian is being written over in an octonionic space, another octonionic space for the next atom, and another for the third atom. So it's like each atom is a universe in itself, which is collectively describing the non-commutative space-time and pre-gravitation as well as gauge fields. So an atom of space-time matter is like an electron with all the fields it produces, electromagnetic, weak, as well as gravitation. The bosonic and the fermionic aspect have come together, as you can see in this Lagrangian, to help us understand what is meant by an atom of space-time matter. Okay, why are octonions interesting? There are only 4 kinds of division algebras which permit division: reals, complex numbers, quaternions, and octonions, denoted respectively by these symbols. The quaternions are 4-dimensional. They have 3 imaginary directions: one real direction, and they're labeled by 4 real numbers. What's nice for us is the Dirac operator is in fact can easily be thought of as a gradient operator on quaternionic space. This, as Michael Atiyah says in one of his talks, the Dirac operator was in reality first discovered by Hamilton when he discovered the quaternions, because, for example, the gradient operator on quaternionic space is just this, where I hat, j hat, k hat are the 3 quaternionic imaginary directions. The square of this gradient is easily seen to be minus of the Laplacian. So, in a similar sense, by extending to the real direction, the gradient operator on a quaternionic space is nothing but the Dirac operator, and its square is the D'Alembert. So this brings us back nicely to this situation, which motivates why we are choosing the Dirac operator as the Lagrangian, because this is the momentum operator, right? This is like momentum. And Dirac operator on quaternionic or octonionic space is like momentum. Its square is square of the momentum, which is kinetic energy, and that explains why this is a very natural Lagrangian on the octonionic space. The quaternions are generalized to the octonions. They have 7 imaginary directions. They are labeled by 8 real numbers. The Lorentz groups have an important connection with the division algebras. SL2C is the double cover of SO13, the 4-dimensional Lorentz group. SL2H is the double cover of the Lorentz group in 6 spacetime dimensions, and SL2O, the Lorentz group in 10 spacetime dimensions. Our bosons and fermions are to be defined on the octonionic spacetime, and more precisely, if we want chiral fermions, on the split bioctonionic spacetime. So, how do we introduce curvature? How do we introduce matter, gauge fields, and gravity in the octonionic space? Just like the metric is introduced on a flat spacetime by replacing eta mu nu by g mu nu, we are now replacing these real numbers by matrices. They are matrix valued coefficient components of the octonionic directions. So, for example, the bosonic matrix QB has 8 matrix valued components going from 0 to 7, all of which are bosonic, and we can do the similar thing for QB dot and similar thing for QF and QF dot. This is how we introduce matter, gauge fields, and gravitation in a unified sense, as in this Lagrangian, by introducing them as quote-unquote curvature of octonionic space. You can see, instead of introducing curvature using the metric on a Minkowski spacetime, we have introduced curvature using matrices on octonionic space. So curvature is being introduced at the square root level, and then you introduce the curvature, and then you take the square. Okay, so we have trace dynamics, we have the Lagrangian, the spectral action principle, we have coordinates. Now we have all the tools that we need to start making connection with the standard model. Octonions, Clifford algebras, and elementary particles. Complex quaternions can be used to generate the Clifford algebra CL2, and which can be generalized to the Clifford algebra CL3 for complex split biquaternions. Given the Clifford algebra, one can make spinors, and in particular from CL2 one can make left and right-handed Weyl spinors, and moreover it is known that CL2 generates the Lorentz algebra in 4 spacetime dimensions. What happens if we replace quaternions by octonions, complex octonions? The smallest exceptional group G2 which is the automorphism group of the imaginary direction of the octonions. It contains SU3 as a subgroup. This is our first hint that the standard model is enclosed in the exceptional Lie groups of the octonions. This can be used to make the Clifford algebra CL6, from which spinors can be made, and it is shown, Fury showed this following the work of many other researchers before her, namely the spinors made from CL6 have precisely those symmetries which are there for one generation of unbroken symmetry SU3 color cross U1 electromagnetic. Quarks and leptons of one generation possessing the standard model symmetry SU3 color cross U1 EM can be obtained starting from complex octonions and by dealing with the subgroup SU3. In this process, one also shows that electric charge is quantized precisely as is observed in the standard model. This is derived, and we note here that the CL6 can be generalized to CL7 if instead of complex octonions we work with complex split biquaternions. So we have electromagnetism and SU3 color, but of course we want to now also have the weak interaction, and we want to talk about gravitation. For that we will need to go to larger symmetry groups F4, larger exceptional Lie groups F4, E6 and E8. Coming back to the Lagrangian, so this is the more precise form of the Lagrangian. It is written on a complex split bioctonionic space, just generalizing the Lagrangian and the action that I showed you in the previous slide. Q1 dot dagger bioctonionic is the sum of the bosonic and fermionic parts. Similarly, Q2 dot is the sum of the bosonic and fermionic parts, and QB dot is made of the gravity part QB dot and the Yang-Mills part alpha QB. Similarly, QF dot is made up of the right chiral fermions LQF dot and the left chiral fermions I alpha QF. Very importantly, we note that the fundamental Lagrangian, assumed to have an E8 cross E8 symmetry, does not contain any coupling constants. It only has overall length scale L. The coupling constant alpha arises when we do this expansion, which is equivalent to a left-right symmetry breaking. A left-right symmetry breaking in the early universe is what gives rise to the segregation of gravitation from the standard model Yang-Mills field. It also gives rise to the separation of right chiral fermions from the left chiral fermions, and it gives rise to the coupling constants. Coupling constants of the theory, like fine structure constant or mass ratios, arise after symmetry breaking. The original Lagrangian is scale invariant, as you can see. It is a length scale, overall length scale multiplying the kinetic energy, but there's no length scale inside here. That's why this is a scale invariant Lagrangian. Symmetry breaking breaks scale invariance, and we have a part which depends on the length L and another part proportional to alpha. So alpha by L breaks the equivalence principle. This part, the gravity part, is independent of L, so that obeys the equivalence principle. This part does not obey the equivalence principle. If we include a mirror universe, then CPT is preserved. Scale invariance is replaced by CPT if we identify along with our universe a mirror universe, so that the original theory is left-right symmetric. It continues to remain left-right symmetric if we assume that there also exists a mirror universe. Our universe violates CP. It also violates T operation. That's how there's a time direction from past to future. But if we include the mirror universe, which is currently hypothetical, then together they preserve CPT. In our universe, CP is violated. That's why there we see handedness in the weak interaction. E8 cross E8 unification of standard model and pre-gravitation. So this is our Lagrangian. We want to look at the particle content of this theory because we know the symmetry group, we know the underlying octonionic algebra. So we can work out what possible branching could give us the observed universe. We showed in this paper that E8 cross E8 admits a branching, as a result of which the following symmetries are realized: SU3 color cross SU2 left cross U1 hypercharge. This is the left-handed sector, the standard model, cross a novel newly arrived at right-handed sector SU3 grav cross SU2 right-handed, to be identified with general relativity, which is what it leads to, cross U1 grav, the so-called dark photon. On a split bioctonionic space on which our Lagrangian is defined, the total number of 496 degrees of E8 cross E8 branch into 248 1, sum 1 248, broken into two separate E8. The first E8 branches into SU3 Euclidean space, which can be mapped to SO10 cross E6. The second E8 branches into SU3 space-time cross E6, which can be mapped to SO19. This 248 can be shown to branch further as 81, 178, 327, 3 bar, 27 bar reps. And this E6 branches into SU3 cross SU3 cross SU3. The first E6 further branches into SU3 left-handed 3 generations cross SU3 color cross SU2L cross U1Y, the standard model. The second E6 branches into SU3 3 right-handed generations cross SU3 grav cross SU2R. SU3 grav is new. This is probably where the conformal gravity modification is coming from. This is identified with GR in the classical limit because of trace d square. And this is a new interaction, U1 grav. U1y relates to hypercharge and then after symmetry breaking to electric charge. U1 grav relates to square root of mass. We have introduced a new quantum number, square root of mass, in Planck units, which is the right-handed analog of electric charge. So electric charge and square root of mass are both emergent after symmetry breaking, and they have the same status in this theory, which also shows evidence for a gauge gravity duality. The right-hand gravity sector is dual in the sense of the Lagrangian and its symmetries to the left-handed gauge sector. So if you can get a feel now for that, we have unified Witten's vector bundle and space-time manifold into a E8 cross E8 symmetry on this bioctonionic space. We have both SO10 and SO19. This is related to the vector bundle, the Euclidean space on which the Yang-Mills gauge fields live, and this will be related to space-time, 10D space-time, from which the quantum to classical transition gives rise to the emergence of four-dimensional space-time. Applications: deriving free parameters of the standard model. So recall, the parameters, the couplings of the standard model arise as a consequence of left-right symmetry breaking. When that symmetry breaking takes place, the original octonionic representations of fermions split into two parts, the left-handed part and the right-handed part. The couplings are nothing but the relative weights of the left and right-handed fermions and left and right-handed bosons. These couplings cannot be free because the original fermionic state was described by octonions, because the emergent fermionic state is also described by the octonions. The relative weights between the left chiral and right chiral fermions are determined by the algebra, and hence the couplings in the Lagrangian are getting determined by the algebra, and that answers the question, how do the octonions without any fine tuning or freedom determine the couplings of the standard model? And we showed that low energy fine structure constant now has a simple expression giving a value which agrees with the experimental value to 2 parts in 10 million. So 0.007297, there's an agreement. Then the next decimal is 3, and here the next decimal is 1. So 2 parts in 10 million, and we have some understanding why there is a discrepancy, because this value is actually on octonionic space in 8 dimensions, whereas the measurements are made in 4 space-time dimensions. In this transition from 8 to 4, because the measuring apparatus is 4D, there is a correction known as the Károlyi-Hazy correction, which can be shown to be such that there will be an exact match between theory and experiment, provided we assume a specific value for the electroweak symmetry breaking scale, which in this case happens to be around 157 GeV. That's a prediction. Similar physics and analysis of the octonionic algebra gives mass ratios of quarks and charged leptons as shown in this diagram. These are simple fractions which reproduce to percent level accuracy the observed mass ratios of quarks, like the heavy top quark, then the electron to muon mass ratio. They can be explained to be a consequence of the octonion algebra coupled to the Lagrangian with the E8 cross E8 symmetry. And so far we have calculated one more observable, the weak mixing angle in the asymptotic low energy value. We get an answer very close to 1 by 4. The experimental value is closer to 0.22. And again, there is some more work to be done to understand how this 8-dimensional number might be coming down to this 4-dimensional measured number once we take account that the apparatus is 4D. Okay, how does the classical space-time emerge from the octonionic universe? Left-right symmetry breaking, emergence of classical space-time, and emergence of gravitation. Critical entanglement amongst fermions. We have so far been describing one atom of space-time matter. The critical entanglement between many fermions leads to the quantum to classical transition because the original Hamiltonian is not self-adjoint. And the emergence of 4D classical curved space-time results from SU2L cross SU2R breaking. So left-right symmetry breaking is caused by a quantum to classical transition in the early universe as well in the laboratory. So the physics is described by this equation. Think of a universe made of many atoms of space-time matter, each of which has its own Dirac operator squared. Classical limit means the matrix, the Dirac operator matrix, goes to one of the eigenvalues. So you get an eigenvalue for each of the Dirac operator, and because these are fermions, they'll collapse to different eigenvalues. And once you have a sufficiently large collection of entangled fermions, you will have many eigenvalues which eventually add up to, because of the spectral action principle, once again it adds up to d square. Sorry, this should be trace d square, which we know is proportional to the Einstein-Hilbert action. So classical gravitation and space-time are recovered because of left-right symmetry breaking and spontaneous localization in the sense of the collapse models of Girardi, Rimini, Weber. And we could ask, why 4D? Why is the emergent spacetime 4-dimensional, whereas the original one is 10-dimensional? We believe the answer has to do with that there are only two complex Clifford algebras up to the Bott periodicity, CL7 and CL3, which admit what are known as spinor representations, the left-handed sector and the right-handed sector. So complex split by causalonions, complex split by octonions. The latter has to do with CL7, which we have been dealing with, and complex split by quaternions are related to Cl3, which in turn is related to a Euclidean space in 4 dimensions and a Lorentzian space-time in 4 dimensions in the right-handed sectors. The spontaneous localization is effectively confining macroscopic objects to the Cl3 sector. Quantums, so only classical systems live in 4D space-time, which we call compactification without compactification. There is no ad hoc compactification need to be done by hand. Quantum systems are always living in a space with E8 cross E8 symmetry. Quantum systems do not live in space-time, neither in 4D nor in 10D. They live in the E8 cross E8 space, which is vector bundle plus the space-time manifold together. That's the arena in which the wave function for fermions has, as well as Yang-Mills bosons, has a non-zero support. The mechanism for the symmetry breaking and the quantum to classical transition is the same in the early universe as well as in the laboratories. That's why we say in the quantum to classical transition as well as in the left-right symmetry breaking, there is no energy scale critically involved. What is important is the degree of quantum entanglement. If you have adequate quantum entanglement, the anti-self-adjoint part of the Hamiltonian become large enough to cause a quantum to classical transition and emergence of quantum gravity, of classical gravity. So that is this emergence shown. So we went down from here by taking the square root and working with trace dynamics on the octonionic space, and when there is lot of entanglement, the quantum to classical transition takes place and we come back to our classical world, the 4D curved Minkowski space-time, on which the vector bundle is then recovered. Whereas quantum systems at all energies and the fermions included live on this complex bioctonionic. So this is a more precise description of the standard model at low energies. It's like in the standard model we are describing water as a fluid. That's the analogy. But in the octonionic theory we are describing water in terms of the molecules which determine the properties of water. So the QFT on Minkowski spacetime is like water as a fluid, and this is the atomic theory level description of water, the octonionic theory description. So suppose in olden times specific heats have been measured, and people say that specific heats can only be measured by experiment, they cannot be derived by theory. Then came along atomic theory and told us that no, specific heats are not arbitrary. The atomic properties of the fluid or the solid determine what value of the specific heat is observed in experiments. So in this sense, the 26 free parameters of the standard model are not ad hoc and just meant for being measured experimentally. They come from an underlying theory which is more precise than QFT on Minkowski space-time, and which tells us that we must describe fermions on a spinor space-time, on a twistor space. That description is more precise and is at the same energy level at which the standard model is currently being observed. Are there any testable predictions of the octonionic theory? No smoking gun prediction yet. Pre-gravitation is mediated by spin 1 gauge bosons. The spin 2 graviton, if it exists, is composite. The neutrino might possibly be massless. Flavor oscillations are explained because the three flavors are spacetime triplets in the octonionic space. There are three right-handed sterile neutrinos. There is an additional charged Higgs boson. Electron and positron repel gravitationally. Holographic length uncertainty relations should be tested experimentally. There are superquantum non-local correlations. A possible explanation for the strong CP problem and origin of matter-antimatter asymmetry. General relativity is being modified by conformal gravity. Could that be the underlying basis for MOND and relativistic MOND? Lastly, much still remains to be done. The other standard model parameters, Higgs mass, W and Z masses, quark mixing matrix, neutrino mixing matrix, QC decoupling constant. The quantum to classical transition, spontaneous localization needs to be understood better. What are the consequences of working with the quaternionic, octonionic spinor spacetime in the context of condensed matter systems? Do we get different predictions? Develop an effective field theory to take account of octonionic corrections to quantum field theory. Understanding the gravi-weak interaction. The weak interaction is the left-handed counterpart of gravitation in this theory. What are the implications for cosmology? Are MOND and relativistic MOND consequences of the octonionic theory? So that is all I have to say. Thank you.